Today we're going to begin the first of 2 lectures on the musculoskeletal system. And we're going to reverse the usual order. I'm going to talk to you mostly about the physiology of muscle contraction today, and then tomorrow we'll move on to how that physiology is applied in the physics of muscle movement and body movement. Basically, the function of our muscles is to provide stability and postural tone to allow us purposeful movement. So we need to be able to stand, we need to be able to hold positions, and we need to be able to go where we want, do what we want. It's also a major regulator of organ movement, so that the smooth muscle in our organs, the autonomic nervous system, can help us move. And it's also a way to generate heat. That's an important aspect of the mass of our muscle, is actually just the generation of heat. We are about 50% muscle in our body. It's one of the biggest masses in terms of weight. We tend to think of bones as heavy, but they're much drier than the muscle. Muscle is mostly water, so it's a great volume and therefore a great mass. We also lose heat relative to the square meter surface of our body, to surface area. We generate heat from our volume, from our mass. So that tends to be a function of the cube of our body, whereas loss of heat is the square. This is why the smaller the animal, the faster the heartbeat to maintain body heat. You have a hummingbird whose heart beats at over 200 beats per minute all the time, because it only has a very tiny mass developing heat and a relatively big surface area for that mass to get rid of it. That's why pizzas cool so quickly. As you go up the line, you get a relatively bigger mass cube to the area, which is the square, and the bigger you get, the more effective that is. So elephants, for example, have a lot of mass relative to their square area. They don't need to generate a lot of heat, and so their heart rates are down around 20, 25. Ours are somewhere in the middle, around 80. So this is a rather important function that we never really think of until you're very, very cold. And what is the first thing your body does? You start to shiver. The shivering isn't your sensation of being cold. It's your body trying to provide more heat by rapidly contracting the muscle to get the heat generated. When we have fever and chills, we kind of get mixed signals. Our body temperature is very high, yet we feel cold, and there's a confusion there. We start to shiver and shake. And we have a very narrow range. We have to maintain, for survival, a body temperature between around 93, at which point your heart stops, and 108, at which point your proteins in your brain will denature and come unfolded, and you'll have permanent brain damage. So the muscle mass of our body is extremely important in this regard. Now, muscles can only shorten actively. They cannot lengthen actively. That's a passive motion. So in order for me to contract and raise my arm, my biceps has to contract. I can't push my arm down with my biceps. That takes another set of muscle. So all our motion is done in muscles that are in pairs. And then finally, muscles are also conductors, just the way nerves are conductors, and they're highly excitable. They respond to electricity by shortening. Now, we have a number of kinds of muscles, and I'm going to go back and do a quick review of that. We have first skeletal muscle, which we've talked about a lot. And the skeletal muscle looks like this. Here is the neuromuscular junction we've talked about. And the skeletal muscle is in sarcomeres, which are lined up in bundles and little fibers the way we see here. Here's the nerve sheath ending on the muscle bundle, and this particular nerve is going to excite this particular muscle fiber. Now, the muscles of the skeletal side are very similar to the muscle on the cardiac side of our body. They look alike, they have different characteristics. Let's look at the skeletal muscles first. Most of our skeletal muscles are voluntarily. They function because of a conscious or volitional control. We don't think about it, but everything we do is and can be controlled from our brain voluntarily. Lots of them we don't think about. We really don't think of our postural muscles, the muscles of our back holding us erect, certainly not the muscles in the back of our neck holding our head up. But if you want to try to prove to yourself that that is really a volitional or voluntary muscle, just think about what happens when you fall asleep sitting in a chair. The first thing that happens is your head falls down because you have lost conscious control of your neck muscles. That usually wakes you up. So almost every skeletal muscle that we can think of has some voluntary component to it. There are a few that don't. The small muscles in our ears don't. Those are completely automatic and we're not conscious of those. Most of the muscles are what we call striped or striated muscle. And they're striated for a very special reason. These muscles, if we focus in here, are compound structures that are made of several elements. And what happens when we get down to the level of light and then low power electron microscopy, we start to see patterns of stripes in these muscles right here. Here you can see elements of the nervous system coming in. There's some lining cells with the nucleus, but we have what are called myofibrils. These are the small units of a single muscle fiber. Now, what these lines are, these are overlapping molecules of the very basic structure that makes the muscle work. If we move down even lower and go to the highest power, we see what are labeled as bands. There's an A band, an H zone, and so on. And these are merely names we've given the microstructure of muscle that we can see now down at the giant molecular level. What we have is two basic elements. One is called actin, and that's represented in green here. And the other is called myosin, which is represented in red. These are filaments. The actin is called the thin filament, and the myosin, the thick filament. And if you look at it very closely, it has little spurs. They both have little spurs. And there's an organization. Here they're held together, the actin fibers, with this so-called Z disc. So they form a unit that functions together. During muscle contraction, what happens is that the two sets of spurs ratchet up on each other and cause contraction. We have only active contraction. Relaxation is passive. Now, this kind of muscle is the most common in our body, and muscles tend to be actually a rather weak substance. They have the power to pull with strength and force, but the muscle tissue itself is easily torn, easily cut, and easily separated. It is not a strong substance as some of the other fibers in our body are. Let's compare this a little bit with smooth muscle. This is a micrograph representation of smooth muscle. And what you want to remember here is that these muscles are only called smooth because they don't have the stripes. When we first examined these under the microscope, we noticed they were different because they were not striated. These muscles tend to have more irregular bundles. They tend to be very long and slender, and they may be innervated by either a single nerve that goes down to perhaps one bundle, and this bundle will contract as a unit, or you can have a multi-unit distribution which scatters to more fibers. And it depends exactly on what you want that fiber to do. How selective it's going to be is how many fibers you're going to have of nervous system attaching to it. Remember, these can also be fired by chemicals directly, such as epinephrine circulating in the system, and they tend to form in interwoven clusters, such as these, and this is what it looks relaxed as opposed to contracted. Finally, we have most of these muscles, by the way, the smooth muscle, for the vast majority, are not under a voluntary or conscious control. They tend to regulate the size and shape of our internal organs, such as stomach, intestine, or the vessels, or our bronchioles. That's where we see smooth muscle. They also tend to be in glands. Glands that secrete saliva, for example, will have smooth muscle that squeezes the gland and ejects the saliva. Finally, we come to cardiac muscle, which is also striped and tends to function very much like skeletal muscle. And it has its Z-disc and the different lines and bands that we saw in normal skeletal muscle. It's arranged a little differently, though. The fibrils tend to not only line up the way these do, very similar to the way skeletal muscle lines up, but it also lines up and joins other bundles in a branching manner, so it tends to have a more coordinated and unit contraction. When part of the heart contracts, for example, in the ventricle, the whole thing tends to contract together. Whereas in your biceps, you can recruit very small numbers for very light weights, for example, or small motions, or more units if you want to recruit them for big motions, heavy weights. The cardiac muscle is involuntary. It is autorhythmic, very much like the smooth muscle, and it functions also as a built-in pacemaker. If you remember, some of the muscles in the cardiac bundle differentiate to become almost purely conduction fibers. So those are the three kinds of muscles we have in our body. The nerve supply to these muscles, almost all of the muscles in the body are stimulated by motor neurons. And the cell body is in the spinal cord of that lower motor neuron. We looked at that in the nervous system. And these tend to go out through the roots, the anterior root, and then go into one of many kinds of divisions and reach the muscle fibers. So here you could fire with a single signal from the upper brain that hit both these nerves. You could fire all 5 of these muscle fibrils, or you could fire 3 or 2, depending on which of these fibers you wanted to hit. The brain can very selectively fire to muscles so that it gets exactly the amount of contraction it wants. All our muscles are very heavily supplied with vessels and capillaries, both arterial and venous. Great deal of bleeding when you cut through muscle, because it's very just saturated with blood supply because of the high energy demands. Now we have something called a motor unit. The motor unit is composed of the motor neuron and the fiber that supplies it, and you may have as few as 10 muscle fibers being supplied by one unit. You may have as many as 2,000. The larger muscle groups, for example, in the back, thighs, the really big ones, would have bigger motor units being supplied by fewer nerves. You don't need fine discrimination in your back muscles. It's a postural muscle. You're either holding up the back or you're not. You're slumping. On the other hand, in the fingers, you've got the finest movements. Same thing with the eyes, the movements of the eyes. All those are regulated where you have much closer to a one-to-one selectivity of nerve fibers going into smaller and smaller units, both sensory and motor. But in our case here, we're interested in the motor unit. So for fine discriminated movements, you want a much closer ratio of nerves to muscle fibers. When a motor neuron fiber fires, everything in its unit fires. Okay, you cannot regulate how much of that unit is going to fire. And the way it works, we have seen before that the motor unit works by firing the small vesicles of acetylcholine in most cases, and in the nervous system, sympathetic nervous system, norepinephrine. We have the synaptic end bulb right here, which is touching the muscle fiber. What nature did not want to happen was for the excitation of the nerve to be continuous. It wanted more discrimination. It wanted this process to start and stop, albeit in microseconds, so there was very definite beginning and the end of every contraction. Sometimes we don't see that subjectively. If we get a cramp in our foot, the whole foot will curl down, the muscles in spasm, but that's really thousands of impulses turning on and off, moving the whole unit the way we feel it, but actually all those muscles are firing separately. What happens is acetylcholine is carried in these little vesicles, literally little packages that are at the end of the synaptic bulb. The nerve impulse comes down here and releases them into a space. If you look carefully, there's a cleft between the end bulb of the synapse and the motor end plate. This motor end plate is a particular part of the motor body. It is not up and down the entire muscle itself. I'm sorry, I said motor body, I meant muscle body. If you look at this side at a close-up, what we see here is we have receptors on these fibers, and these receptors are geometric receptors ready to accept the chemical acetylcholine, here shown as little diamond-shaped pyramids. They fit into these, and when the acetylcholine hits the ACH receptor, it opens a channel, and sodium, which is high in the extracellular fluid, rushes in with its electric charge, and that's what we call the depolarization potential. Now, immediately released is acetylcholinesterase. That's the enzyme that breaks down the acetylcholine and stops this from happening. It's, again, a millisecond response, and the entire process stops. And there is something called a refractory period. There is a period in which no further stimulation of any magnitude, electrical or chemical, will open up those receptors again and make the muscle fire. What's happening at that point is the muscle is repolarizing. It's pumping out the sodium, and it's reestablishing the sodium-potassium balance, the plus-minus charges on its membrane, so it can fire a second time. And that refractory period is a very real fixed period of time as to how much time it takes to get all this repolarization done. But we have millions of fibers in all of these, and they're not all firing together. They're firing at different times. If the brain stimulates a muscle hard enough, it will again appear to us as if the muscle is firing all together. It's called a tetanic contraction. And for example, if I were to electrically stimulate my arm so it was even more than my brain was doing, if I stimulated those nerves, it would sit there and do that, just constantly firing full power until there was exhaustion, and you would have what's called post-tetanic collapse and relaxation. Now, in the firing of muscle fibers also, you have to have relaxation of the opposing muscle. If I fire my biceps, it requires that I relax my tricep. That's all involuntary. We also know that our muscles have these stretch receptors in them. So from a practical point of view, if you want to stretch your muscles the way we do before exercise, you should not be doing it quickly. For example, we're always told not to bounce when we're trying to touch our toes. But because we have these stretch receptors that you saw when we talked about the knee-jerk reflex, the spinal reflex, and if those get pulled quickly, they will make the muscle contract. If they get stretched very, very slowly, the muscles will allow themselves to relax and go to a greater length. If we move along now and talk about the kinds of muscles we have, because they're not all the same. In the last about 2 decades, we've discovered that there are several types of skeletal muscle, and it involves very similar chemical reactions, but with very different results. And people say, oh, I'm a good sprinter and my brother's a good long-distance runner, are quite right. They have different kinds of muscles, and I'd like to tell you about those. The slide that shows this best is the ADP-ATP energy cycle. This is one of the most fundamental cycles of energy production in the body. It's common to very, very many different kinds of energy production. And I've saved it for here because it applies very well to the muscle contraction that we're studying. If you look at this slide, we have two chemicals. One is called adenosine triphosphate. The other is adenosine diphosphate. Think about a rock being pushed up a hill to the top of a mountain. When you have adenosine triphosphate, you have a potential energy in this molecule. If we release one phosphate, the process releases energy and is able to do work using other small molecules. So if we perform work, we release one phosphate from this molecule, and the result is adenosine diphosphate plus a free phosphate in solution. It's as if we took the rock at the top of the hill, gave it a push, and let it roll down. We have converted potential energy to actual kinetic energy, the energy of motion. When it reaches the bottom of the hill, it has expended all its energy. We do the same thing here, only in this case, we have a chemical energy that is potential. The release of the phosphate releases energy into its environment, and work can be done. Now, work in physics and in chemistry is defined very specifically. Energy is the ability to perform work. Work is moving any object any distance in physics. Theoretically, if I take this pencil and I put it over there, I've done more work than if I stood against the wall and pushed with all my might for an hour. Because when I haven't moved the wall, I haven't done any work. Now, that's theoretical, because I've probably done work inside moving my muscles, but I think you'll get the idea that we have to do work with this energy. Then when we get to this state, which is at the bottom of the hill, we've got to get the rock back up to the top of the hill so we can do it again without using other resources and discarding this. So we reuse the ADP, and we use energy to attach the phosphate. We get this energy from the burning of glucose and other energy stores. These are the fires that give us the energy, the heat. So this cycle from ADP to ATP is continuously going on in many of our body's cells. It's the prime source of our getting work done, moving molecules, attaching them, unattaching them, and so forth. And muscle is one of the great users of the ADP-ATP cycle. Now, what are the different kinds of muscles and how do they work? The first type we discovered were the type 1 fibers. This is all skeletal muscle. When you look at the muscle, you can't tell them apart. These are physiologic differences. We call these slow oxidative fibers. These are also called out in the world of athletics slow twitch fibers. They tend to be very fatigue resistant. They work slowly, they move slowly, they're strong, and they are resistant to fatigue. They tend to generate the ATP for the restoration of their energy aerobically, meaning oxygen is used in the process. This is very efficient when you use oxygen to burn your fire and to get energy. So the ATP that we see in that cycle is split off very slowly. The muscles contract slowly and they regenerate slowly, but they can go for a long period of time. These muscles are generally our postural muscles, the neck, the back, and the ones that are used for small range of motion, not very rapid changes, and long periods of time. The same muscles I told you were in the back of your neck to hold your head up until you fall asleep. Those are the type 1. They are the slow twitch oxidative fibers. We have two types of type 2 fibers. Type 2 fibers are type 2A and type 2B. These fibers are fast twitch fibers. And these fibers the A fibers are somewhat fatigue resistant. They're kind of like the type 1 fibers, so they tend to be able to go on for a long time. They also generate ATP aerobically. They split it rapidly and the fibers contract rapidly. So they're very similar to type 1, except they're faster. And they're less fatigue resistant than the type 1s that we talked about. So they're kind of in the middle. These are the sprinter's muscles. These are the strong calves and thighs that drive a sprinter down the track. They're very, very fast, and that sprinter can probably go for some distance. We then move to the type 2B fibers, and these are fast twitch B fibers. They fatigue very quickly. They are glycolytic fibers that use glycogen to break down and get sugar quickly. They generate the ATP anaerobically. This is not an oxygen-dependent cycle, so they're borrowing some energy for later repayment when we can get oxygen into the system and rebuild the energy cycle. These are usually the big muscles of the arms. They can generate a lot of power, but they will tend to build up something of an oxygen debt. Now, the muscle categories we talked about are assuming you had very clear-cut divisions. As I said, when you look at the muscle, you certainly can't tell what kind of fibers they are. You can actually check under a microscope and see some characteristics. And if you did biopsies on your calf, your back, your shoulder muscles, you would see differences. You would also see differences between individuals using the same muscle. So those people who say, I have a greater ability to sprint, but I'm really not a long-distance runner, are probably correct, because almost all your muscle groups are combinations of type 1, 2A, and 2B in different proportions. The muscles of different people vary from birth. You are endowed with a native ability to do different types of performances, either in athletics or work, by what combination of muscles you have, by your body habitus, and you are to some extent able to change this. So this mixture is not set in stone. The shoulders and arms are used in short bursts, so they need more of the type 2B, but if you did something like repetitive long-distance rowing at a lower level, you would actually change the proportions of your muscles. You could not overcome your nature entirely, but you could certainly make it different. The large muscle groups in the legs that we're going to show you in detail next time, they need both postural fibers, because you're standing and supporting this low level of contraction all the time. And sometimes these can be trained, though, to have fast twitch fibers, so you could be a sprinter as well. And different exercise programs will do this for the athlete. Muscle fibers get their contraction at their greatest stretch. So when you stretch fibers a little bit, short of that sudden stretch reflex and not overstretching them, when we set muscle fibers up at a slight stretch, they'll get a more powerful contraction. And this contraction can be maintained for long periods of time. We get pathologic situations in which the brain may fire for too long a period of time, or inappropriately, or non-selectively. So there are examples in physiology, for example, in epilepsy. We've talked about grand mal epilepsy, when the brain is just firing the whole brain at once and all the parts of the body are contracting at once. This is the patient having a seizure. That patient will often develop very characteristic positions based on the strength of the muscles. There's one position is called opisthotonous, in which the head is thrown back. You'll see the patient on the floor, but they will often be up on the back of their skull, because the muscles of the back of the neck are far stronger than the muscles in the front. They're firing both at their maximum, but they are overcome by the muscles that are thrown back. Now, the muscles of the arm are another one, and we see this very typically in patients with spastic paralysis. You'll see the patient in this position, because, again, the adductors of the arm are stronger than the abductors, and the firing of both will keep them both in here at the side. The flexors of the arm, the biceps, tend to be stronger than the triceps, so the arm is pulled up. What we call the pronators, which turn the palms over, are more powerful than the supinators. So the hand is turned into this position. And then you might wonder why the fingers are straight, because the flexors of the hand are stronger than the extensors, but with the wrist forced down in this direction, the extensor tendons are pulled so hard, and you will see paralyzed patients often in this position. They have a spastic paralysis, not a flaccid paralysis, and this gives us the very typical picture of that kind of muscle apposition and opposition, and shows us very clearly which are the strongest muscle groups. Now, muscle tone is measured in a couple of kinds of activities that we are interested in. We have what's called isotonic and isometric contractions. There's been a lot of interest in what will build muscle bulk better. Isotonic contraction means the same tone, the same tension. So if I take my arm and put here a 50-pound weight and I pull it through this range of motion, the force against the end of my hand the entire time is 50 pounds. So that's iso, meaning the same tonic. The weight, the tone, the force that my muscles are exerting is not changing through the entire range of motion, up or down. Isotonic contraction. Isometric contraction means that the length, metric means measure, the length of my muscle will stay the same. Now, if I reach under the table and press up with all my might, starting from a slow pressure to higher pressure, I actually have no idea how much force I'm exerting by this muscle. I can start very lightly with a few pounds and go and go and go until I really break out into a sweat and squeeze as hard as I can for as long as I want. My muscle hasn't changed its length at all. The amount of tone is changing all the time, so I am varying the tone, but I'm keeping it isometric. If I were to have a strain gauge, a very sensitive gauge that didn't lengthen, where I could pull up and measure how much I was exerting, I could know on a dial exactly how much pressure I'm putting on those muscles. But again, that'd still be isometric, because I'm not changing the length. The question is, which of these will build muscles more? Many, many years ago, we all read comic books that had Charles Atlas ads in them, and Charles Atlas had this program of isometric exercises, and you would buy this book so the bullies wouldn't kick sand in your face anymore. What his whole program was a series of isometric exercises that required no equipment. So you would go muscle against muscle. I would have my two hands together, press up with my right hand, not have any movement, but have an isometric contraction of this bicep. This hand would have an isometric contraction of my tricep. And I could generate huge amounts of pressure if I were willing to push hard enough without any equipment there and without any change in the length of either muscle. Could then reverse that, turn it over, and he developed this series of exercises that would build muscle without equipment, could be done anywhere. And he was on to something at the time. He understood that there was something very important about this type of exercise in building muscle. It built a great deal of strength. It didn't necessarily build bulk, but it built a lot of strength. There was another factor that we haven't realized until recently, and that was something called concentric and eccentric exercises. When I perform an exercise in which the angle between the two limbs decreases, we call this concentric. Now, this angle is shortening my muscle, and it is bringing the angle tighter in. And then when I go down, I have an eccentric motion. I am increasing this angle and lengthening this muscle, although my muscle is still contracted. So we now call this positive and negative repetitions, but if I'm curling a barbell, This is my concentric or positive part of the repetition. And as I go down, if I don't let it go down quickly and slow it down, I'm still holding that same weight. This is an isotonic contraction because the weight is the same in my hand. My muscle length is changing. But as I go down, I'm still holding that isotonic weight all the way down to the bottom of my repetition. For some reason we don't understand, the eccentric or negative repetition is more damaging to muscle than the positive. And what the weightlifter is trying to do is to damage muscle during this exercise to a certain extent. This is why weightlifters usually don't lift weights to the same muscle every day. They'll usually go every other day. The reason is they're trying to damage the muscle a little bit, both up and down, and create injury that can then be repaired. The body then comes in and repairs the muscle, perhaps better than before if you give it enough protein, energy, and time. And so this is how the lifters build both bulk and strength by constant damage and repetition. However, you have to be very careful because it's a very fine line between destroying muscle, rebuilding it better, or creating an injury that's not going to heal as well. We also have the difference between regular, repeated, low-level activity, which is aerobic activity, such as jogging or swimming, in which an oxygen-rich blood is able to perform the energy under what's called aerobic conditions. We can keep up with our oxygen consumption. People who are involved in these activities can generally regulate the rate at which they wish to exercise by what we call a conversational jog. They will keep that rate at such a level that they can talk comfortably without getting out of breath while they're performing that activity. That's actually a very good measure of aerobic exercise. The anaerobic exercise, such as weightlifting or sprinting or stop and go activities, basically builds up muscle protein very well. It builds up mass very well, but it also has the problem of being more damaging to muscle and making you more susceptible to injury. Today, it's recommended that people concentrate on a combination of both, depending on the sport they're training for, the age of the athlete, and their physical ability. Now, interval training is another solution to this dilemma of how exactly one should train. It's a way of combining both anaerobic and aerobic exercise at the same time. What one can do either cycling or running or rowing or any other repetitive activity. You can take a segment, let's say a mile of bicycling at a certain aerobic rate, and combine that with then an interval of very anaerobic activity, such as a sprint, and then go back to your aerobic rate and keep alternating your intervals of hard and less hard activity. This seems to be very, very beneficial for a very wide range of activities. And lots of different athletes at all levels are training this way. We also have noticed an increase in interest in anything that has gravity involved in it, such as upright sports and weight training. Apparently, the effect of putting tension on the bones, the muscles after all are attached to bones, and using gravity against the force and weight of the bones is very good for the bones themselves. People and athletes of various kinds who, as they age, tend to lose bone density can find themselves reversing that problem and increasing or maintaining bone density as long as they're doing activities that involve either gravity or hard weight training. So people lifting weights, using exercise machines, being in an erect posture, so that playing tennis, squash, basketball, all of these force the body to work against gravity and the pulling of the tendons on the muscles, on the bones themselves, exerts an effect that causes the bones to maintain calcification and density. The opposite of that would be swimming. In swimming, you're in a zero gravity situation. The body is being held afloat, and the only muscles getting exercised, although there are many, are those that don't have much to do with fighting the forces of gravity. Swimming is an excellent aerobic and anaerobic sport. It's very good conditioning for the heart and lungs, but it does almost nothing for the bones. So people who choose to swim for many reasons, there are lots of people who, as they age, have arthritis problems, have joint injuries, and being in a state of suspension where gravity isn't too much of an issue is very good for them. And while I wouldn't recommend that they give up swimming, because that is a very good form of exercise for the cardiovascular system as well as specific muscles, it is something you really should combine with another type of exercise, for example, weight training, so that you can get the benefits to the bones. So there's been a great popularity in weight training, and for other reasons. Muscle at rest, sitting even at your desk, just burns more calories per minute than does fat. Fat is not a very metabolically active tissue where muscle is. So even if you're doing nothing but lying still, you will burn more calories if you have a higher proportion and bulk of muscle mass than you do if you have more fat. So people who have taken the time to do bodybuilding and training find it easier to keep their weight under control than people who are fatter and have a higher proportion of fat. It's a positive cycle that allows you to stay more fit if you keep your muscle built up, and that's another reason weight training has become so popular. And finally, one of the areas of interest that has become very important lately is physical fitness in the very elderly. It has always been assumed that as one gets into the later decades of life, you lose the ability to gain strength and to gain muscle mass and performance. So that patients in their 70s, 80s, 90s, and even 100 were thought to be on this downward slide of physical fitness. Patients were bedridden, they fell a lot, they became more sedentary. A group of investigators went into nursing homes and started training these elderly people. And what they found was fascinating. It's very easy to find out exactly how much progress you're making. You can measure muscle mass easily. You can also determine total body fat versus muscle mass easily. And most simple of all is you can tell that a patient who could do 6 repetitions of X amount of weight can now do 12, has doubled their performance, at least for that muscle group. So they took very elderly patients, some as old as 100, and started them pumping iron in the nursing homes. They had a very careful program followed by the doctors and a steady but determined progress for these patients in all their muscle groups with free weights. And what they found was that it was all a myth. You can build new muscle in the elderly patients, you can build mass, and you can build strength. And it's valuable to do that. They found that the patients who were bedridden were very often no longer bedridden. Patients who were walking around with walkers and canes got rid of their walkers and canes, and patients who were falling down all the time stopped falling down. They regained balance, they regained excellent postural tone, and their whole quality of life had improved. So this has become a whole new area of weight and strength training, has gotten rid of one of the real destructive myths of conditioning, and improve the life of a lot of people now in a world where we're having an enormous number of people living to those older ages. That's all for the physiology of muscle. Next time we'll take a little look at the physics of muscle movement and then a description of the muscles in the body.